So we've kind of just walked through an awful lot of this. We're going to take a look at what the H&D curve is here in just a bit, if we have time, and how it applies now. So we used to have to chart our processor chemistry and how exhausted it was, and that was the foundation for the H&D curve. We don't do that anymore, but we still use it as a visual, and we'll talk about that here in a bit. So traditional screen speeds, I kind of talked about that. In the transition from, slow to high speed and high speed to CR and CR and PR. So how screen speeds, how we manipulated screen speeds were, we had inside of the screen, we had these things that were sensitive, there were phosphors that were sensitive to X radiation. So we make an exposure, let's see if I can find these. Yeah. That's an awful picture. I thought I got the entire eclipse, and I got like half a second of it. And so that was just me being goofy. I said that's a pocket eclipse, because everybody thought that, I'm just trying to move on. Everybody thought that the world was going to end because of the eclipse. So I coined it the apocalypse, and that was the whole thing right there. I thought I got the whole thing from start to finish of the eclipse, and no. Okay, shut up. I want to say that this was a physics, a previous physics playlist. Maybe here. So what I did was I went down to the lab, and we've still got some screens down there, and I made exposures on those screens so that you could see what the technical factors did. Okay, I'll tell you what I'm going to do. I'm going to search these out. I'll find them and I'll put them into Canvas so that you can see them. So what happened with our screens is our films were light sensitive. Okay, so they're sensitive to all different kinds of light. Different manufacturers had safe light options. So Kodak, for example, worked off of a green spectrum. Well, what's green?
Green screen.
Green screen, yeah. But what is the color green? How do you get green? Blue and yellow, right? It's blue and yellow. So it was sensitive to blue and yellow light primarily. It wasn't sensitive to red light. So whenever you see in a movie somebody's processing, films, you see in a movie that they're in a dark room and they're processing the films, and they've got a red light. That's because their film is most sensitive to green and yellow light. So it's affected by the phosphors, but it's also influenced by KVP. If you increase KVP or you increase mass, what you get then is an increase in the glow of the screens. So the higher, the more those screens glow, the more density you put on the image. Okay, so that's screen speed. Film speed is the same thing. The film speed primarily was affected not just by the chemistry in the screens, but the thickness of the chemistry. How much chemistry did you put on the film? So we'll kind of walk through this. last semester in physics, what we did was we took the films and we put it inside the intensifying screens. The intensifying screens, the light in the intensifying screens is really what exposed the film. And then we took the film and we put emulsion on both sides of the film and used 2 intensifying screens, right? So all of that increased film speed. Sensitive to radiation and light, and they had to be spectrally matched. Okay, so we had 2 basic types of films. Kodak made one, and I forget who made the other one. But Kodak was sensitive to sensitive to green light. You know, so the screens would glow green, and the film was sensitive to that green light. The other one was sensitive to, I want to say, primarily yellow light. And so they could use, blue light. So they could use either a yellow or an amber safe light, or they could use a red light, either one. Okay, so the point to all this is if you used a Kodak film inside of the other cassette, then it's going to be less efficient because it's only going to pick up those blue light waves, right? So they had to be spectrally matched, and what that means is the right film with the right screen so that you optimize the amount of light that you're going to visualize and how dark the image is going to be. So sensitometry is a study of the effects of exposure on and processing on the image. We can measure optical density and contrast, and that's in the characteristic curve. It's also referred to as the H&D curve, which is also referred to as the sensitometric curve. So we're going to walk through that real quickly, and then we are going to leave it there. Okay, so I'm going to turn this off. We'll talk about the H&D curve. So what we would do is, oddly enough, not make an exposure on the with the screens of films. We take a film out of the film bin and expose it with some of the stuff we got back there in that cabinet, a sensitometer. And what a sensitometer does is it exposes the film so that you can see, once you develop the film, you can see kind of like a step wedge appearance where densities go from so dark you can't see through it to so light you can't detect it. All right, so it's like 21 steps, each step a little bit darker than the other. So what we'd do is we'd make an exposure with the sensitometer and we'd process it, and then we would kind of catalog, measure the light that's coming through each one of those steps, and then catalog how those steps would chart on, like a graphing paper. All right, so really sensitometry was to detect whether or not your chemistry was still good or if it was bad. So if we had exhausted chemistry, what we would get is a loss. You make the perfect exposure that should demonstrate you good contrast and density, and what we would have is a lower density, probably a funny color on the film, and less contrast. Okay, and that would indicate that we need to change the chemistry, just flush the whole system out and start all over again. But let's assume that the chemistry is good and we're using, most of your departments would have at least 2 different speeds of image receptors, screens primarily. So the slow speed screens were, for the reasons we talked about before, inherently higher resolution, but they were slower too. They gave us less contrast, higher resolution, and we had to use a greater exposure factor in mass in order to make the exposure. For example, if I made an exposure on a hand with a 400 speed system, I might only need 1.5 mass on a 400 speed system. On a high speed system, I'm going to need low speed system rather, detailed cassette, I'm going to use twice as much. It is 200 speed as opposed to 400 speed. So what we get then is on our H&D curve, once we plot all those different densities, we measure the light that's coming through the film, and what we would get is a curve that looked like that. Okay, again, this is H&D curve. Harder and dry field, sensitometric curve, D log E curve, and the reason it's D log E curve is this is a density axis, and this is the exposure axis. So as you would expect, if you increase your exposure, you get an increase in density, right? You would think that there would be a direct relationship between exposure and density, and it really wasn't. If you had a direct relationship, then for every unit of exposure, your unit of density would go up exactly the same, and what you would have is not a slope, but just this line that goes, from minimum density to maximum density at a constant rate at a 45-degree angle. All right, so your DR systems are actually like this. The more exposure you get incrementally the same amount. This exposure gives you the same amount of exposure. That doesn't relate to the contrast that you see. All right, so when we have this very vertical H&D curve like that, what it means is we're going from an area that's very light to an area that's very dark with very little exposure in between. Okay, so what does that sound like? Dark or light to dark? Contrast. Contrast, right. So if you go from light areas to dark areas very quickly, then that's naturally going to be a high contrast image. So our 400 speed systems were kind of like that. Our slower speed systems, our 200 speed systems, drug that density out over a broader area. Okay, so where you're looking at H&D curve, first off, your exposure to your image receptor on a digital image receptor looks like that. Okay, that's just your exposure. In image processing, what you're going to see are the computer algorithms are just going to be these lines that look like this. If you were to get into your computer algorithm and you look at your lookup table and the computer algorithm you create whenever you make your exposure, it's just going to be lines you can't make any sense out of. Okay? So what they do is for the stored computer algorithm, that is your lookup table, they assign a H&D curve to it. Okay? It's just a visual is all it is. It doesn't really mean a whole lot except for if this computer algorithm had this H&D curve next to it, what could you say about that algorithm?
It ran off of a slow hour.
This one ran off of a fast, high-speed, high-contrast image receptor. Okay? So this would associate with things like hand x-rays, extremity work, things like that. Okay? So this one, on the other hand, being more horizontal, so a very vertical H&D curve indicates high contrast. A horizontal H&D curve then would indicate low contrast. So things like chest x-ray, you want to bring the natural contrast, the anatomical contrast down some, so that it's not as stark and it doesn't look like ribs. It looks like a chest x-ray instead of ribs. So this would be associated with chest x-ray, extremity work. Okay, so there's three portions of the H&D curve. So what we have at the bottom, you look down at the ground, what's the first thing that you see that's attached to your body?
Toes.
Toe, right. So that's the toe portion. This would be the shoulder portion. And then this area through here would be the straight line portion. The straight line portion describes your contrast. To a degree, it describes your speed. The straight line portion closer to the density axis, in general, not always, but in general, indicates a higher speed. Okay? So vertical, contrast, close to the density axis, high speed, horizontal, low contrast. further away from the density axis, low speed. Straight line portion, useful densities. Toe portion, your exposure's so low that you really can't, you lost contrast. Shoulder portion, exposure so high, you also lost contrast, useful densities. H&D curve in 4 minutes. Okay? So again, you may see this on a test, and you may be asked, the specifics of 2 H&D curves, but what they really indicate is what kind of computer algorithm are you applying to the exam type. So you push chest x-ray and you want to see ribs. This is what you should have applying to your exposure. This is what you are applying to your exposure. Not optimum. Can you see the ribs on chest x-ray? You can, just not real good, right? You shoot a hand and you push chest x-ray button, then you're going to be applying that to what should have that, right? So you're going to lose contrast. That's your control of contrast. KVP is not your control of contrast. That's your primary control of contrast. What computer algorithm are you applying to your range of exposures?
H&D.
Well, yeah, it was.
Yeah.
I ended that kind of on a high inflection, like I was looking for a question. It was really a statement. Your contrast is going to be determined by essentially what button you push. Chest x-ray for ribs, or chest x-ray for chest x-ray versus, chest x-ray for hand. Your contrast is going to be controlled by that. And these are just visuals for that. Any questions?
So on the test, is it going to ask, what's the best control of contrast? The answer would be H&D curve?
No. In context of the H&D curve, what I might ask is which one of these two is inherently higher contrast?
Okay.
This one.
But you're not going to ask,
You're not
in,
good.
measuring contrast.
No.
It's which one has more contrast, which one is better for low contrast.
Low contrast, yeah. Which one's faster, maybe? That would be really the speed is a point, and it's irrelevant at this point. But really, whichever one's closest to the density axis. The full explanation or full answer to that would be at 1.0 plus base plus fog. But so somewhere around this point right here, whichever one's closest to the density axis. And out of these two, the high contrast. And we can have high contrast, like mammo films look like this. Very high contrast, but very slow speed. Okay. Any questions?